In this video, I'd like to run through the notes for Unit 2, Part 1, Lesson 2 of our college algebra class. And in this set of notes, we're going to be discussing what it means to have a function that is even or odd, and when functions are increasing or decreasing. We'll talk about what that means too. So to start with this notion of even and odd, functions can be even or odd, much like numbers can be even or odd, or neither for that matter. And a function is considered even if the function evaluated at the opposite of x is equal to the function when evaluated at x. And here we've got a picture of a graph that actually exhibits this behavior. Let's say we're talking about an x value of 1, for example. If I were to evaluate this function at 1, it would have a y-coordinate, or an f of x value, up here. I don't know what that number is, but it's somewhere up here. It's associated with this x value of 1. If I jump over to this side of the graph and take a look at the x value -1 and consider its function results. Now here again, this function is now evaluated at -1, and this function is up here at this level. Well, whether I evaluate at f of 1 or I evaluate at f of -1, these two both have the same y components to their coordinates. The y coordinates are the same. So in this case, f of -1 is equal to f of 1. And that's true for any x value on this graph. If I were to pick an x value here and consider its y result, well, those two would be on the same level, and so on. For any x value, I could evaluate the function at the opposite of that x, and the y values would be exactly the same. This is what we call an even function. Now for an odd function, this time when we evaluate a function at the opposite of x, the result ends up being the opposite of the function evaluated at x. This example exhibits that behavior. Let's pick another x value. We'll scoot out a little bit further this time and say that our x value here is 3. Well, the position for 3 is right here, and so the y coordinate associated with 3 would be represented by the calculated result, f of 3. If I jump out to -3, down here, the function result wouldn't be the same. That would be an indication of an even function. This might be the shape of an even function. But in this case, the function result ends up being the direct opposite of the y value from f of 3. So f of -3 down here happens to be the opposite of the function when evaluated at 3. So let's say this y value, let's say this y value was 4 when x was equal to 3. Then over here, this y value would have to be -4. It's the opposite of the other. And that's true for any x value on this graph. If I had an x value here and took a look at its y value associated with that x, and if I took a look at the opposite of that x and its y value down here, this y value in this position is the exact opposite of the y value in that position. So this is an example of what we would call an odd function. Now this example in the middle we would say is neither even nor odd, and a simple or a single counterexample would be sufficient to indicate why this is not even and why it's not odd. So let's choose this x value right here. I'm not really sure what it is, but f of x is the y coordinate right here. F of x is equal to 0. If I were to choose the same position on the left side of the equation to represent f of -x, we can see that the y value associated with this position way over here is not at all the same as this one here. F of -x is not equal to f of -x. Moreover, and I'm going to have to jump down here to fit this in, f evaluated at -x is not the opposite of f of x either. And while this definition was our definition for an even function, and this one was our definition for an odd function, neither one holds true in this case. So if neither definition holds true, then we would say that the function itself is neither even nor odd. So a lot of times if we're looking at pictures, we describe what an even and an odd function looks like. And we often use geometric terms to describe this. And with an even function, we would say that an even function, this guy here, is simply a graph who's reflected over the y-axis. If I were to graph one leg or one component of this and then reflect that image over the y-axis, here, we would see a mirror copy on the left and the right. And a good description for our odd functions is that we rotate the graph 180 degrees about the origin. So again, if I had one leg of the graph completed, and if I were to rotate all of these coordinates 180 degrees, if I were just to flip this thing, not flip, but rotate 180 degrees, this leg of the graph would land right on top of this one. And the rotation has to occur about the origin in order for this to be considered odd. In this graph here, we sort of have that rotation occurring. We have, a leg or a branch on this side, and in a sense you might see that it could rotate around and land on this section of the graph. But since that point of rotation is here, not here at the origin, that doesn't satisfy our description. So again, we would say that this graph represents a function that is neither even nor odd. So if we have a graph to look at, then determining symmetry isn't too much of a challenge. However, sometimes we won't have graphs to look at, and other times it's nice to have algebraic proof to describe whether a function is even or odd. And if I didn't make myself clear here, I think I glossed over this. When we're talking even and odd, we're talking about even and odd symmetry. So let's use the definition to determine whether or not these functions are symmetric, and if they are, we'll determine what type of symmetry they will exhibit. So the test for symmetry is pretty straightforward. As with the definitions above, the test was to determine what happens when we evaluate the function at the opposite of x. So what I would like to do is I'd like to take this original function and evaluate it at negative x instead of just x, and then simplify. So f evaluated at negative x in this case is a negative x squared minus 5. And you probably recognize what's going to happen next, but I'll just be explicitly clear with the math. This negative x squared means to multiply negative x times itself. And when we multiply negative x times itself, we're just going to end up with a positive x squared again. Well, this expression, x squared minus 5, that's just the same as the original function, f of x, isn't it? And so the work that we were showing was indicating what happens when we evaluated at negative x. So if we evaluated this function at negative x, and it ended up simplifying and equaling the original function again, what does that describe? Well, that describes even symmetry. We can confirm that with the sketch of a graph, because the function f of x equals x squared minus 5 is simply a standard parabola shifted 5 units down from the origin. And whether you pulled this up on a graphing calculator or if you remember your graphing rules from Algebra 2, the picture would look something like this when drawn correctly or sketched correctly. And certainly this graph does have even symmetry. There is a reflection across the y-axis. In Part C, we can do the same thing. We'll come back to Part B in just a moment. Let's evaluate h at the opposite of x. And here again, that means to substitute the opposite of x in place of x in each of these cases. So h of the opposite of x, so h of negative x would be 5 times negative x times negative x times negative x. Again, I'm just doing this to really make this super clear as to what's happening. Now, if I had 3 negative x's multiplied in a row, a negative times another negative ends up being negative. And we have 5, so we have this negative that I'm going to push out front, the 5 that remains, and then an x cubed. So we've got negative 5x cubed plus x. Now, I don't know about you, but I recognize that this thing doesn't look like h of x like we saw before. So I'm comfortable in saying that it's not even at this point. This function is not the same as this function, what we started with. So I know it's not even. If it's not even, I want to check to see if it's odd, and if it's not even and it's not odd, then I can say that it's neither or neither. So here's what we can do next. If we know that it's not even, go ahead and factor out a negative 1 from that group. What would happen if you factor out a negative 1? If I divide this term by negative 1 and this term by negative 1, what is left? Well, in this case, this first term divided by negative 1 is positive 5x cubed, and dividing this term by negative 1 is negative x. And so now we can say that h evaluated at negative x is this thing. But take a look now. We have the original function on display right here inside of our grouping symbol. So algebraically, we've shown that h evaluated at negative x is equal to the negative sign in front of h of x. And that is our definition for odd. So we knew that the function was not even based on what we saw here. But by factoring out a negative 1, we were now able to say that this function is odd. And if we plotted this function on a graphing utility, we would see a shape that looks like this. And this shape certainly does exhibit the rotational symmetry that we were after. So by using algebra, we determined that this was odd, not just that it was not even, but it was actually odd. In this first example, we were able to show that it was even. So let's take a look at part B here. So we'll substitute a negative x, or the opposite of x, in place of x. This negative x cubed, well again, that's 3 negative x's multiplied together. That's going to be a negative x cubed, and we have minus 1. So we've simplified, and we see that g of negative x is this expression, which is not exactly the same as the original. So if it's not exactly the same as the original, we know that it's not even. And if it's not even, we'll go ahead and factor out a negative 1 to see if it's odd. And after we factor out a negative 1, we're left with positive x cubed. That's a good sign. But after we divide this second term by negative 1, we get a plus 1. And this result is not the same as what we started with at the beginning either. So we would say that this function is not odd. Well, if we've established that this function is not even and it's not odd, then we would say that it is neither even nor odd. And if we were to take a look at the graph, or if you remember how to graph a cubic function from your Algebra 2 days, you might see something that looks like this. It's a bit of a snake graph. It does have rotational symmetry, but it's not rotational about the origin. So since it's not rotational about the origin and it does not have reflectional symmetry across the y-axis, then the picture or the image of the graph also indicates that this is neither even nor odd. So I think that's a good stopping point with this video. We've covered even versus odd and how to determine them with a graph or using algebraic methods. In the next video, we'll talk a little bit about increasing and decreasing functions. Thanks for watching.